Hey everybody, this is Mr. Ainsworth, and we are going to get into Activity 1B1 extension practice on closure. So let's read the directions here. Let's get started, and let's go for it. Here we go. All right, for each of the following, provide either supporting examples, okay, or counter examples, okay? Now, counter examples are examples that show something is false. Remember that. All right, supporting examples show that it's true. Counter examples are examples that show that it's false. So in the first one here, we want to consider the following set of numbers here, which is called the natural numbers here. Some people call them the counting numbers. It's the natural numbers. All right, denoted by this symbol here, the capital N with two vertical lines. And they go from 1 to infinity. So this set right here is from 1 to 2 to 3 to 4 and so on, all the way to infinity and beyond, as Buzz Lightyear used to say. You know, just got to throw in the kid stuff here. All right, I'm a dad. That's what happens when you're dad. Okay, so what we want to do is show that the naturals are closed under these operations right here, one at a time. And so each one of these is its own thing here. And what we want to do and test to see if a natural plus a natural is a natural. Is a natural minus a natural a natural? Is a natural divided by a natural always a natural? Is a natural times a natural always a natural? That when you think about the closure question, all right, it's all about closure. That's our main theme. Okay, what you need to think is that if you operate on any two numbers in the set, is the result in the set. That's the main idea. All right, so in this case, all right, is a natural plus another natural, because we're dealing with addition, right? That means plus, addition here. Is that equal to a natural? That's the big question. All right, and what you do is you can explore, you can provide supporting examples. Okay, so let's do that. Let's explore. All right, when I say explore, I'm talking about throw down some examples, right? Show some supporting examples here. So what do I mean? Well, let's take any two naturals. All right, let's take 2 and 5, and let's add them up. We get 7, and guess what? That's an element of the natural set. Okay, remember the symbols here in set theory, okay? So this means element of. Element of. Now, if you don't know what that means it's in the set. Okay, in the set. All right, fancy words for saying in the set. So when I say 7's a element of the naturals, I'm saying 7 is a natural number, which is obviously the case because the naturals go on to infinity. Okay, even though we just start the pattern 1 through 4, 1, 2, 3, 4, etc. Obviously, it's increasing by 1, and so 7 is a natural number. All right, that's the first set of numbers that you ever learned when you're a youngster in elementary school. Okay, so what else is true? Well, is the natural numbers closed on the subtraction? Well, I don't know. Let's try it. So if I say, well, let me write down the question. So is a natural minus a natural equal to a natural? That is the big question. All right, and if you explore, okay, as I keep on saying here, which means you play with numbers here. If you take 5 minus 2, you get 3. All right, that is a natural number, so I can say it's an element of the naturals. If I take 10 minus 4, I get 6, and that's an element of the naturals. So it seems like if you subtract two naturals, you get a natural, but you got to be careful with this one because if you take 1 minus 4, you get negative 3. So I'm going to say but. All right, 1 minus 4 is equal to negative 3, and that is not an element of, okay, if you slash it, that means not an element of the natural set. Okay, so you got to be careful here. This is called a counterexample. Okay, a counterexample, an example to show something that is false. Okay, it is not true that a natural minus a natural is always a natural. It's sometimes true, but not always true. Okay, so keep that in mind. Now, how about this one? Next one is a natural divided by natural is, okay, is that equal to a natural? I'm going to put a question mark here. I should have put that in red. So let me put that in red. So is a natural number divided by a natural number always a natural number? Question mark. Okay, well, let's test. All right, and this is what I mean by explore. Explore it. So if I take 4 divided by 2, I get 2. All right, that's a natural number. Okay, it's an element of the naturals. If I take 6 divided by 4, I get 3 halves. All right, and that is not an element of the natural set. Okay, sorry about that, guys. Gotta turn off my phone volume. Okay, so this is not a natural number because the natural numbers do not include the fractional numbers, the rational numbers like 3 halves. There's all kinds of counterexamples here. So right here, we can say that it is not closed. Okay, so it's not closed. It's called a counterexample, not closed. In fact, you know what? I forgot to write that down on the previous one. So it's not closed under subtraction, so I'm going to say no. Okay, not closed. I forgot to write that down. All right, so exclamation point, not closed under division, not closed under subtraction, but it is closed under addition because when you take a natural plus a natural, you always get a natural, like 3 plus 8, well, that's 11, and guess what? That's natural. All right, so this tells me that it's closed, all right, under addition. I forgot to write down my conclusions. Okay, so it's very important that you write down your conclusions, by the way. You have to say whether it's closed or not closed. So in the first one here under addition, it's closed. The second one, it's not closed, all right? Because, well, 1 minus 4 is negative 3, and 3 is not natural. Okay, so you got to say it's not closed. Okay, you can't just provide a counterexample. You got to make a statement, guys. You got to say closed or not closed. You got to be bold. You got to be courageous, okay? And you got to say whether it's closed or not closed. And you got to either provide supporting examples, or you got to provide counterexamples which show that it's not closed. So either one. Now, in terms of multiplication, if I take any two naturals like 2 and 4 and I multiply them together, you're going to get a natural. All right, 3 times 5 is 15, and that's natural. These are elements of the natural set. Okay, you can test any two numbers. You can take any two natural numbers, and a natural times a natural is always a natural. So a natural, in fact, let me put this in red. So a natural, all right, times, use parentheses here, times another natural, all right, always equals a natural number. So in this case, all right, it is closed. All right, under multiplication. We use the word under. Under multiplication. You always have to specify the operation. All right, just don't say it's closed or not closed. Say closed under whatever operation you're dealing with. So it's closed under addition. It's not closed under subtraction. It's not closed under division, but it's closed under multiplication. These are my conclusions. So you got to provide supporting evidence when you deal with closure. Okay, it's not good enough to say whether it's closed or not closed. You got to back up what you're saying. All right, and you got to back it up with numbers, examples. And so when I say explore in this class, I'm talking explore numerically. Okay, provide numerical supporting examples to prove your point, or counterexamples to prove that it's not closed. All right, and by the way, it only takes one counterexample to do that, as we talked about in class. Okay, number 2. Number 2 is different. Now, here we have a new set. Now, this is not the natural set. When you go from 0 to infinity, 0, 1, 2, 3, 4, to infinity and beyond, okay, this is called the set of naturals including 0. Or you can think in grade school, we used to call these the whole numbers, okay, in grade school. But it's the natural numbers including 0. That's all it is. And it goes from 0 to infinity. This ... means to infinity and beyond. It never ends. It's an infinite set. It's the opposite of finite, okay? There's not a specific number in there. It's an infinite set, okay, because it never ends. And we want to see if this set's closed under subtraction and division only. Okay, so if we take any two whole numbers here, subtract them, do we always get a whole? So the question is a whole number, all right, minus a whole number, okay, always equal to a whole number? Yes or no? And the answer is no. Okay, I'm going to say no. Why? Okay, well, if you pick two of these and subtract them, you get a negative number. Okay, so 2 minus 4 is negative 2, which is not an element of this set. Okay, it's not an element of the whole number set. Okay, it's not a whole number. It's obvious. You can provide a lot of counterexamples of that. How about 1 minus 5? That's negative 4. Okay, that's not a whole number either. Okay, there's a whole lot of counterexamples here. All right, because of that, all right, it's not closed. Okay, under subtraction. That's your conclusion. All right, so what we did is we provide numerical examples, all right, to prove our point. You can't just say closed or not closed. You got to back it up, guys. You got to back it up with evidence. All right, and the evidence in mathematics typically is numerical. All right, and so when I say explore and write down your evidence, I'm talking about numerical examples. Now, is a whole number divided by a whole number always a whole number? So here, the big question is a whole number divided by a whole number, is that always equal to a whole number? And the answer is no. Okay, all right, because if you just take 1 divided by 2, you get 1/2, and that's a fraction, and that's not a whole number. All right, so the counterexample is 1 divided by 2, all right, is not an element of the whole number set. Okay, you can just say it's not a whole number, or you can say 3/5. You can use any two whole numbers you want, divide them, you get a fraction, and it's not an element of the set. So because of that, it's not closed under division. So I'm going to say not closed under division. Okay, so you have to make a statement when you're done. Okay, it's either closed or not closed, but you got to state why. You have to provide numerical evidence to your claim. So if you claim that it's closed, then you better have a good reason why. We call that supporting evidence. That's why when I say explore, write down the numbers. If you think it's not closed, you better provide a counterexample. So it's you either provide examples to show that it's correct, like I did here, okay, when it's closed, or you provide counterexamples like this one here, all right, to show that it's not closed. All right, so you got to provide evidence. You can't just say closed or not closed. That's not good enough. Okay, you got to show your thinking. Now, let's switch to the set of integers. Okay, so this is a big set, a very important set of numbers called the integers. It happens to be the whole numbers here. All right, these are the whole numbers. All right, and their opposites. All right, these are the opposites. Obviously, the opposite of 1 is -1. The opposite of 2 is -2. The opposite of 3 is -3. So we call the -1, -2, and -3 opposites of the whole numbers. So when you put the whole numbers and the opposites of the whole numbers in the same set, you get something called the integers that you've seen since grade school. All right. Now the question is, are they closed under addition, subtraction, the square root operation, and the factorial operation? So let's deal with it. So is an integer plus an integer an integer? So the question is, all right, is an integer, all right, plus an integer equal to an integer? That's the question. That's what you need to be thinking when you deal with what's called closure. In this case, that happens to be. You can take any integer, add it to an integer, and you always get an integer. So for example, -3 plus 1 is -2, and that's an integer. 4 plus -5 is -1, and that's an integer. All right, so here I'm going to say it's closed under addition. Closed under addition. Okay? Now, subtraction, let's find out. So my question is an integer minus an integer equal to an integer? That's the question. And if it's true, then it's closed. If it's not true, well, then it's not closed, right? So let's test. -3 minus 1 is -4, and guess what? That's an integer. All right, 5 minus a negative 2. I'm just making these integers up, by the way, and I'm subtracting them. Look at the minus sign. All right, that's equal to 7. That's an integer too. It always is an integer. So an integer minus an integer is always an integer. So I'm going to say that it's closed under subtraction as well. By the way, these are big results. Okay, you got to remember all these things. These are basic results. Think of them like axioms, truths. All right, they're always true. And you can't prove this, by the way. This is just always true because you cannot come up with a counterexample. It's impossible. All right, but not the case for the square root operation. Here, so if you square root an integer, okay, if you square root an integer, is that equal to, I put a question mark there, is that always equal to an integer? And the answer is that it's sometimes true, which means it's not closed. Okay, so sometimes it's true. Like if you square root 16, you get 4. Okay, that's an integer. Okay, remember Z means integer here. Integer. All right, if you square root 25, you get 5, and that's an integer too. So it seems like it might work, but if you square root the 2, okay, that is not an integer. Okay, it's not. Remember, if I slash the E, that means it's not an element of, which means it's not an integer. Okay, it's an irrational number. This is called an irrational integer, or an irrational number, excuse me. And because, and even a negative, like if you square -1, you get I. That's an imaginary unit. Okay, so there's a lot of counterexamples here. So I'm going to make a big statement. I'm going to say not closed under the square root operation. So not closed under the square root, okay, operation. That's my conclusion right there. So always have to make a statement right here. So in the first two, the integers are closed under addition because an integer plus an integer is an integer. The second one, an integer minus an integer is always an integer, so it's closed under subtraction. Square root operation, not so. If you square root of 2, you don't get an integer. Square root negative number, you don't get an integer, you get an imaginary number, so it's not closed. And remember, all you have to do is provide a counterexample. Okay, now in this one here, is it closed under the factorial operation? And so let's analyze. 4 factorial, it gives you 4 times 3 times 2 times 1, which is 24. 3 factorial is 3 times 2 times 1, which is 6. They give you this example right here. All right, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. All right, but it turns out that factorials are only defined on positive numbers. Okay, factorials, and you can research this, just Google online. Factorials are only defined for positive numbers. Keyword positive. Okay, so -1 factorial is undefined, and because of that, it's not closed. So it's defined when n is positive, but because integers can be negative, like -1, -2, -3, -4, it's not defined all the time. And if the set of integers was closed under the factorial operation, then it would be defined on all the integers, and that's not the case because integers can be negative, and factorials are not defined on negatives. They're only defined on positives. Okay, and there you go. All right, that's a little tutorial. Not little, that was actually kind of big here. In which case I went through all the examples of the extension practice on closure. Okay, now remember, this is a video, and I went over a lot of different examples here. And if you don't fully understand, what I suggest you do with any video of mine is watch it again until the light bulb goes on. Okay, so work hard, practice, make yourself proud. This is Mr. Aynesworth here. You can call me the Aynes, okay, or Mr. Aynesworth, Mr. A, whatever. Okay, I'm from Great Oak High School, okay, Great Oak High School in the Temecula Valley, and I will see you in my next lesson. Take care. Bye-bye.